Good morning. So in this video, I'm going to tackle the different crystal classifications of metals. So generally, there are three crystal classification of metals. FCC, the face-centered cubic, BCC, the body-centered cubic, and the hexagonal-centered uh, crystal. So we're going to tackle those three crystal classification of metals. Let me share the PowerPoint. Okay, so the first question is, why do we need to study the structure of crystalline solids? The answer is, a knowledge of crystal structure for iron, for example, help us understand the transformation that occur when steels now are heat treated to improve their mechanical properties. So when you are producing steel, it involves high temperature and then you cool it down. So it's quite important to understand the formation of crystal on how fast are you going to cool the steel, what is the optimum temperature. No, because this will affect the strength and the properties of the steel. That's why we we study the crystalline solid structure. Sa glasses naman, production of glass ceramics, it involves the formation of a glass that is subsequently transformed into a crystalline solid and then into an amorphous solid. So paiba-iba siya ng ng state. So that's why it's also important in the manufacture of glass, yung structure ng crystalline solid. Nagiging liquid din yung glass, liquid, crystalline solid, amorphous solid. So that's why it's important to study the structure of crystalline solid. So what are crystals? How can you tell whether a structure is crystal or it's amorphous? No? So it's common sense naman. Parang when you see something na transparent o kaya regular yung kanyang structure, generally we call those as crystals. So a crystalline material is one in which the atoms are situated in repeating or periodic array over large atomic distances. So yung natin, yung mata natin, hindi naman makikita yung mga atoms. Pero there are some devices, like for example, X-ray, that can see the atoms, and mga electron microscope, they can see the atoms. And then if there are regular arrangement of atoms, we generally that translate into a crystal. Nagkakaroon ng crystal structure yung material. Makikita natin sa mga susunod na slides. All metals, generally are crystals. Many ceramic materials are crystals, and certain polymer form crystalline structure under normal solidification condition. Tandaan nyo yun, all metals are crystals. Many ceramic materials and certain polymers are crystals. What are unit cells? So unit cells, these are the atomic order in crystalline solids, indicates that small group of atoms form a repetitive pattern. So yung mga paulit-ulit na arrangement ng atoms sa isang material, yun yung tinatawag na unit cell. So you're going to learn more about this unit cell as we go along. So first, we're going to discuss the metallic crystal structures. So I've mentioned this in the introduction, ano? The FCC, the face-centered cubic, the BCC, the body-centered cubic. Pag sinabing face-centered cubic, nasa unahan yung center atom. Pag naman body-centered cubic, if we're going to imagine a cube, nasa center siya ng cube, yung center atom, ano? And then we have the hexagonal HCP, ano? We have a hexagon. Ibig sabihin, when you say hexagon, it's a six-sided polygon. So you have 6 atoms, tapos it surrounds a atom in the middle. So that's why this is hexagonal, no? So we're going to see illustration of this metallic crystal structures later. Okay, so first let's consider the face-centered cubic crystal, or FCC. So as you can see from this illustration, ano? The central atom, actually, this one is on the face. If you're going to consider this is the face of the cube, you can see that this center atom is on the face of the cube. So that's why this is called a face-centered cubic. Probably you can also consider this illustration, and as you can see, the center atom, this one, is on this plane, on this face, no? And also that atom, and that atom, and that atom, and that atom. So this is how a unit cell of a face-centered cubic crystal is arranged. Ano? We're going to check this in an X-ray device. We're going to see that the atoms of the metal is arranged in this way. Aside from the center face atom, you have 4 atoms that surrounds it, on the corners. So in electron microscope, you can see that the arrangement is something like this. This is your center atom, and then this is the 4 atom that surrounds the center atom. Even if you look at on this side, you have the center atom on this plane. On that side, on the top side, you have the center atom. I hope you can you can distinguish this particular crystal and other crystal later. So example of this are aluminum, copper, gold, and lead. So generally these are at room temperature. Nagbabago-bago kasi yung crystalline structure at minsan nga nagiging amorphous pa ng different metals. So, temperature dependent to. We're speaking here of at room temperature, aluminum, copper, gold, and lead. Okay. So generally this is characterized by kasi it's a cube, so by the length of the side of the cube. So this is A. This is the length of the side of the cube from this atom to that atom. This is defined as the length of the cube A. So the cube edge length A and the atomic radius R. The atomic radius is the diameter of the atom divided by 2. That's the atomic radius. Okay. So this is the equation for A in terms of the radius. A is equals to 2R times the square root of 2. So let's try to derive this equation for cube edge length A in terms of atomic radius R. So what is important for the derivation of the cube length A is this illustration. As you can see from this illustration, you have 4R, the total diameter of the cube. I'm referring to this as the diameter is 4R. So this is the diameter. So this diameter is 2R, and then as you can see, the edges atom contributes an R or a radius. So that's why this is 4R. 1R, 2R, and another R. So this is 4R. And then this is our cube length A. So just by using the Pythagorean theorem, so A squared plus A squared is equals to 4R squared, quantity squared. Ano? So if you're going to solve this, you're going to have 2A squared is equals to 16R squared. So basically, if you're going to transpose 2 on the other side, and then you're going to take the square root of this term, you're supposed to get 2 times R times square root of 2. So that's how you solve A. You can easily confirm that. Ano? Let me annotate. I'm going to try to derive this. Ay, magkaksak na. Bunutin yung butin yun. Hugutin mo. Tapos, yan. Saksak mo. So, coming from here, so you will have 2A squared, and then 4R squared is similar to 16R squared. So if you're going to divide this by 2, you will have A squared equals to 8R squared. If you're going to take the square root of this term, so that would be 2 times 4. Ano? 8 is 2 times 4, square root of 2 times 4. So that's why you will have 2 square root of 2. 2 times 4. Then you have the square root, and then you have an R. That's the square root nito. So that's why the square root of 4 is 2. So that's why you have 2 R square root of 2. It's quite easy. No? I hope you can follow the derivation. So what about the volume? The volume of this unit cell. Of course, obviously, the volume of this unit cell is a cube. So if you're just going to get the cube of 2R square root of 2, so 2 times 2 times 2 times 2 would be 8. And then the square root of 2 is 2 square root of 2. So 8 times 2 is 16 right here. R cubed times square root of 2. I hope you get this one. It's quite simple. Ano? Okay. Okay. So another property of crystal is the atomic packing factor, or APF. So APF is defined as the volume of atoms in a unit cell, divided by total unit cell volume. So yung total unit cell volume, yun yung A cube na dinerive natin kanina. Yung 16, just remember that? 16 R cube times square root of 2. Tapos yun namang volume of atoms in a unit cell. For example, in FCC, how many atoms do we have in a unit cell? So if we're going to consider this drawing right here, you will have 1 atom, then another 1 on the bottom, tapos on this side, you will have 3, yung dito sa face na to, tapos yung sa kabila, so 3. Tapos, this looks like, ano, what is this? 1/8, no? This is 1/8. 1/8 of an atom. So, you have 8 of this. So, that's one atom. So, all in all, we have 4, no? We have 4 atoms. 1, 2, 3 is visible, 3 hubs is visible, and the other 3 hubs are, because in a cube you have 6 sides, di ba? You have 6 sides in a cube. So 3 hubs are visible, and then the other 3 hubs are invisible. So you have 3 atoms, and then you have 1/8, 1/8 of each in each corner. So that is 1 atom. So you have 4 atoms. So just calculate the volume of atoms itself is you have 4 atoms, volume of 4 atoms divided by the total unit cell volume, which is 8 cube. No? So for APF, this is equivalent to 0.74. So let's try to derive this. This 0.74 atomic packing factor for FCC. Show that the atomic, this is example problem 3.2. Show that the atomic packing factor for FCC crystal structure is 0.74. So we're just going to use the definition of atomic packing factor. This is volume of atoms in a unit cell, VS, total unit cell volume, VC. So I have already shown you that we have 4 atoms in a unit cell in an FCC. You know? And then the volume of a sphere is 4/3 pi r cubed. So just multiply this by 4 and you will have 16 over 3 times pi r cubed. Okay? And then we earlier derived that the total volume of the cell is 16 r cubed square root of 2. Ito yung a cube, ano? Yung sinolve natin last time. So we just get the quotient of these two. So 16 over 3 pi r cubed divided by 16 r cubed square root of 2. So as you can see, you'll be able to cancel out r cubes. No? You can cancel this out. And then you can use your calculator, you know, to calculate 0.74. You can also cancel out 16. You can cancel out 16. So that would be, let me check. That would be 1/3 pi. It would be 1/3 yun, 1/3 pi, tapos square root of 2, divided by square root of 2. Okay, so my calculator is showing us it's equal to 0.74. Yeah? Also, I hope you can confirm that using your calculator, 0.74 for FCC. Okay, so let's take a look at some other metal crystal structure. The next one is BCC, or body-centered cubic. So as you can see, the central atom is inside the body. It's not on the plane or the face of the cube. No, it's inside. Okay? It's inside. So it's different from FCC. No? We're going to take a look at this image right here. It's between. It's inside, no, the unit cell. Example of this is iron and chromium at room temperature. Okay, so A, still remember A is the cube edge length. A in terms of radius is 4r divided by square root of 3. So basahin nyo lang sa libro, hanapin nyo yung exercise, probably ibigay ko sa exam, o sa exercise nyo kung paano ito dinerive. Dinerive ko na sa inyo yung una. So more or less may idea na kayo kung paano ito dinajustify, no? Diniderive. Hanapin nyo lang sa libro. Derivation. And then, the atomic packing factor for BCC is 0.68. No? So, mas konti yung atoms dito. As you can see, di ba? As compared to FCC. So, mas mababa yung kanyang atomic packing factor. So, you can also derive this. Ang importante dito para mag-derive nyo to is, syempre, kailangan nyo rin yung radius drawing dito. So, tingnan nyo kung makikita nyo sa libro. No? Para mag-derive nyo itong 0.68 na to. I hope you understand what is the difference between an FCC and a BCC. Ito nasa loob yung central atom. Ano? Yung kanina, yung BCC, yung FCC nandito siya sa plane, sa face. Okay, and then the last one is the hexagonal closed pack crystal structure. So as you can see, sabi ko naman sa inyo, yung hexagon, 6 na side na polygon. So meron tayong 6 na atoms, tapos napapalibutan niya yung isang atom. So that's why this is hexagonal closed pack crystal structure. Tapos dito sa second layer, 3 na lang. Tapos hexagon na naman dito sa ilalim. Ano? So example nito ay titanium at saka zinc. So more or less, hanggang dito na lang muna itong video na ito. Ano? Okay, so see you sa next video. So tingnan ko kung makakahanap ako ng exercise para dito sa video na ito. Topic na ito. Ano? Metal crystal structure. So FCC, BCC at saka HCP.